Well, today I want to talk about a kind of self-attention which could be used for question representation and also question answering using that beautiful paper of TransferNet. So you're all familiar with GRU. And so before I begin this lecture, you should be familiar with biGRU attention that I have explained in my playlist for machine translation. So let's continue. So I assume you're familiar with GRU. It's very simplified type of recurrent neural networks in comparison with LSTM and those things. And so LSTM is powerful. LSTM is very, very powerful. I use it for many projects. But GRU is fast because it has less parameters. So there is a reason for everything. Why it is fast? Because it has less parameters. And that's why you see in many problems, even in the original paper of machine translation, biGRU used GRU. And so that's why this is important. So with the same analogy that we had with biLSTM and those things, we can create biGRU, forward, backward. And if you can also combine BERT with biGRU, because BERT is a good representation of your sentence and so on. And you can also use the idea of dropout to make your model more efficient, easier to train, and so on. And the idea of biGRU can be combined with the attention. But there are two major attention in my opinion. Cross attention, I call it, like machine translation. You are translating from English to German, and then you have the encoding representation of encoder, representation of decoder, and then you create that scoring function, and from score you create the attention and so on. But here, because we have just one sentence and nothing else, we are not talking about any other sequence, just one sequence. Because in machine translation we have two sequences: sequence from the source, which is English, sequence from the target, which is German, and so we give it to this to the encoder. This is the encoder, and we give this to the decoder, and using these data we create attention and so on. But so this is cross attention. There are two types of attentions, and self attention. But self attention is the idea of today. But people are not familiar with self attention because it is something that, for example, in TransferNet they used this idea of self attention. So you see that we can have many different configurations. You can put convolution layers after attention layers. And so the idea of embedding the question is interesting. You have a question, you want to embed it. Well, there are lots of ways to do it. You can use autoencoders. I will explain it in a different playlist, autoencoders in NLP. And but this way is easy. You can just use your simple sequence, simple recurrent neural network, and just one of them. For example, one encoder. There's no need to create a decoder because we have just one sequence. And so we represent it like this. After giving to the encoder, so we have some representations of that. But if you remember in the biGRU attention, we give in order to calculate this score. B is a score, sometimes called energy, sometimes called aligning, and so in order to make this B, which is B is just the weights of the I call Q here. Let's call it context. because it's linear with the same analogy to that Bardano attention in machine translation. We can say that Q here, Qt, is a context because it's a linear combination of your hidden representations. So how do you find B in this way? Because we don't have any other sequence other than one sequence, unlike machine translation that you have two sequences, sequence for source and sequence for target. But here we have just one sequence. So how do you do that? Well, we say that we need another things, but we can say that we can use, just like transformers, they have queries, keys, and value. So 3 times you're using your original sequence. So that's why we are using these keys. So we can think about it like the keys in the transform model. But if you're not familiar with transform model, doesn't matter. You can still enjoy this because QKT can be just a function. And when we say function in our deep learning, it means a neural network. So it's a neural network, but your input is Q, and there are some parameters in your neural network which we call it theta of your model. Now you have the keys. Now you can have dot product, and after that you give it to softmax, so it becomes the weights, and Q is the context. And the implementation is very easy. First, for encoding, for example, here I've used biGRU, and then for any whenever you need word2vec, you just use an embedding, because number of words is the number of words in your vocabulary. They are just some integers, 2, 3, 6. But this one-dimensional object should be mapped to a dimensional. You should learn the word2vec embedding online. I mean jointly. If you don't have any pre-trained model such as GLOV 100D, which is 1 gigabyte, you can just learn it. It's not difficult. Instead of doing word2vec separately, you can just do it here, everything here. So this is the idea of NN embedding. So it's just a layer, just a linear layer, but goes from 1 to the number of dimensions. So inside that embedding, you go here, you map it to projection to create a one-hot representation, and after that you give it to a linear layer to create the dimension that you want. For example, here the dimension is dimension of the word that you are interested. For example, 30, and then you give it to. Then you have dropout, and then for embedding, you can use this encoder question.encoder that you give the keyword embedding to that. And here is Q is the context, BI is the weights that we have calculated using this. As I said, that the dot product of your hidden representations of encoder, which is one sequence only, and to the keys. But keys here are just our own our original sequence, but we have learned how to represent it. So it's a kind of self-attention. So this is self-attention. And then, but here you have learned everything, but you need to know something about the gold answers, about the labels, so that you can use your classical supervised learning. And for that, you can, in different problems, you can use different outputs and labels. For example, in the problem of question answering, if you're familiar with my lecture on TransferNet, this beautiful article about question answering that uses the idea of self-attention, then uses this idea. So we represent our model, we represent our question like this. You give it to the encoder here. As I said, this is the keys, and the dot product of the keys and your hidden representation becomes the weights here, the weights of the representation. And so it's a linear combination of your hidden representation. And so you have a very beautiful representation Q of t. So now Q of t is ready. Now Q of t is ready to learn these W's, the scores of entities and relations. If you remember that article, then because we have lots of, it's a multi-hop reasoning. We have a knowledge graph. If you remember, we had a knowledge graph. We had multi-hop reasoning, and that's why when you jump from one node, one entity to the another, and then another, it depends on, so it's a stochastic process here. Then if you multiply it by this W, which we have learned that because G is again a neural network, it's a function of what you have represented for your question. So theta is just the parameters of this G function. And then because you have W, you can multiply it with A, but A is not still enough. A, what can you do with it? We should compare it to a linear combinations of your A of t, because t could be this t from 1 to t could be in 3 hop. It could be a 3 hop reasoning, but in complex question answering, maybe sometimes you have 5 hop. So depending on that, you can use different t. And now we have the goal solutions. Now you have the goal solution, and what you have predicted, here is why you have predicted, and that's why you have a loss. And since we have loss, you can backpropagate it to everything you had, to all the parameters you had. You can use this loss to backpropagate the error to all the parameters that you have. For example, this theta of G are your parameters that you can learn, and also your parameter theta ft. These are another thing. So once you get the loss, you can backpropagate and tune these weights in order to have a better loss. And so for different epochs and different batches inside each epoch, you run until your training loss is reducing and your validation loss is reducing. That's why this is converged and ready to be published. And another way to think about attention is that article that I explained. So there are 2 ways to implement the cross attention, but this is something else. Now I'm talking about cross attention, the usual thing that you do for the machine translation, attending source, relating source into the target sequence. So we have 2 sequences. So there are 2 ways. One of them is global attention model. The other one is local attention model. In the global attention model, at each time step, the model infers a variable length alignment vector, A of t, based on the current target state and all source states. So a global context vector, C of t, here, this is the global context, is then computed as the weighted average according to A of t. But the local attention model, the model first predicts a single aligned position, P of t, for a current target word, a window centered, so we have a window centered around the source position, P of t, is then used to compute a context vector, C of t. You may think that this is non-differentiable, and you will, if you read that article, I think I've explained it before, but if you read it, you will see that these 2 are different ways you can implement cross attention.